I'm going to try it. Evelyn Duesterwald.
Very
They're excellent and a very long, impressive looking title, so I'm just going to stop talking and let her talk.
Yeah.
Thank you.
Yeah, so this is some work that we are doing that's in the space of tuning applications, which I already mentioned earlier. And it's done as part of the PERCS project. Vivek mentioned already the PERCS project, which is a large government project, and where we experiment with these ideas. And this is work done with a team. Okay. Oh.
Nope, just enter.
All right. So what is the problem space that we are looking at? So we all know we can no longer rely on technology to give us performance improvements. At the same time, our software complexity is growing every day. Every day there's more virtualization, more standardization. We add more layers to the execution stack, and complexity is growing as we sit here and look at this. And so what this also means that we no longer can take this approach where we sort of expect, okay, we get new hardware in the next generation, and this is going to speed up everything else for us. Similarly, we can no longer take out another layer, software layer, optimize it in isolation, put it back in the stack, and then expect performance improvements to show up. As complexity grows here, the performance problems really show up in the interactions of those layers, and not so much isolated optimization is not going to gain us that much anymore. So we really have to look at a new approach if we want to gain more performance out of this situation. And that is where we have to look at everything working together, tune the entire execution stack, and not look only at one of these layers, just at the application in isolation, line it on the side and put it on the stack. So the themes that are really important to get these additional performance improvements are vertical integration, across the execution stack, certainly adaptivity. We cannot really look at this problem until we have all of these layers together running. And also the notion of continuity. The situation is clearly changing. It's not a static situation. Different environment conditions show up. The application has phase behavior. So we have to keep looking at this problem. We cannot assume that once we are on our highest optimization level, we no longer have to look at the code. We have to keep reconsidering the situation and keep retuning the application. So that is the overall frame. And so we started this project that we call continuous program optimization to address these issues. And the real key here in doing anything like this that looks at the entire stack is certainly that we can monitor and understand what's going on. We mentioned several times already that the complexity debugging these systems is so hard because we have all these layers running at the same time. So the real challenge is in understanding the performance interactions among those layers. And then we look at this tuning optimization process as a two-way adaptivity. On the one hand, we now looking at the application, we're really interested in improving application performance, and we like to tune it to best exploit its environment and the current resource availability in the environment. But we also like to look at adapting the environment to best serve the application's need. So there's sort of a two-way process. And there's certainly, in adapting the environment, we have to look at shared resources. So there's certainly some tension here. We'd like to address both of these. And so, as I mentioned already, the key in achieving this kind of adaptivity is performance monitoring, environment monitoring, understanding what is currently going on in the system. So that ultimately we can, operating in this continuous loop of tuning the application, monitoring what did we do, what has happened, what are the new triggers in the application and the stack. So here there are a couple of what we call CPO scenarios that we like to target. And so here first in the category where we're adapting applications, we're looking at library tuning. As part of a PERCS project, we work with people in Cornell and Illinois that have done some work in tuning libraries to the actual execution environment. MPI, also look at communication libraries. We had a project over the summer tuning the MPI library to choose the appropriate message protocol based on the actual length and frequency of messages. We also currently have a project tuning the JIT compiler. And so here we are targeting a lot of the heuristics that usually hard-coded in throughout your JIT code. One example that we're starting with is inlining decisions. And we'd like to take out this heuristic, this control, and make this dependent on performance information and environment information and control in that way. We also like to export this tuning environment up to the application writer to address algorithmic tuning, which is sort of out of our reach. And so if we offer this environment where we can evaluate our current tuning version and experiment with different other versions to the application writer, we can also reach out to algorithmic tuning on that level. Now, in the other category, where we're adapting the execution environment, this has also been mentioned. There's certainly been a lot of work done in the past in adapting GC policies. Heap size is also a resource coming from outside from the operating system. And these, in a way, are still fairly controlled because typically you run one application inside a VM or one VM per application. It gets more interesting if you look at more sharing, if you look at resources in the operating system that are shared among multiple applications. Here the trade-offs are much more interesting. So there's one question, understanding what is my best resource, and then there's also the RSS to trade these off among all the applications that are running. And here right now we're currently looking at page sizes, and at the end of this presentation I have sort of some snapshots from a demo that we're looking at. Currently architectures are offering more and more different page sizes, but we don't really have a good handle on what is the right page size to use. You cannot just always go with the large page size, because if your application actually only has a small hot section that is not occupying all of these large pages, we actually pay a lot extra, especially if there's more memory pressure from other systems. So this is an interesting tuning example. Okay. So the overall architecture that we are building is, if you're looking here at a stack, we have what we call CPO agents that look now at one of these scenarios. For example, if you have the JIT tuning scenario, we have an agent that's actually sitting inside the Java virtual machine and making tuning decisions there. So we don't expect there's going to be one module that does all of this tuning. If you're looking at shared resources, you're sitting in the operating system. If you're looking at JVM tuning, we're sitting there. So we in fact have multiple of these agents dedicated to a tuning task. But they're connected because they're all communicate and monitor a system through this vertical performance and environment monitoring layer. So this is how each of these tuning agents understands what is the effect of transformations across the system. And this is also how we can communicate, because a tuning transformation is an event, a performance event, that we can issue on this vertical performance monitoring bus here. So we have ultimately multiple CPO agents. We're currently working on one in the JVM and one in the operating system for page size. Okay. And so what we started building is now this PEM layer and developing exactly what this is. And building it as a platform, with a platform-independent API. So we can build the CPO agent that requests, this is the kind of monitoring information that I need. And do this in a platform-independent way so we can at least port these CPO agents and tie PEM on itself to the platform. So we built PEM to both to serve for online performance monitoring to the CPO agents, but also to serve as a standalone performance understanding tool. So in this case, we don't service the information only to the agent. We actually write it out to a trace file and visualize it for performance understanding. And that's certainly also what we need in order to develop these agents, to understand what is actually going on. So we've built this tool for both of these purposes. So the PEM infrastructure consists of three components. We first have the event specification. So this is one repository, one central place where we define all the events in the system that we are interested in. If you want to add a new application software layer that has its new performance events, for example, a new library, maybe a communication library, we have new events. We add more event specifications in this repository. The specifications are written in XML to have a language-independent format. And we also, at this level, describe the semantics. For example, for communication events, we'd like to know that sends and receives are matched. This is information we define at that level. Then the next component are a rich set of tools where we generate language-dependent data structures from these XML definitions. Data structures and header files, and we're currently supporting Java, C, C++, and Fortran here. And these are now used to build the rest of the system. For once, we generate header files for the layer instrumentation. In order to issue events, we instrument a layer, for example, a communication library, and send and receive points. We issue events into the PEM library that a send and a receive has occurred. And so for this instrumentation, we generate the header files